10 conversations in which the late Jacob Bronowski related to George Steedman his personal account of the discoveries and problems of the 20th century. Last week, Dr. Bronowski described how components and events at a subatomic level cannot be described exactly. This week he finds how simple atoms build up into the complex structures of life. The programme is introduced by George Steedman.
One thing they'll find in our skulls in our generation, which I think was not present in previous human generations, certainly in the West, was that chronic awareness of war and the likelihood of personal involvement in death and destruction goes right back to 1914-18.
That's true.
And, of course, came to a climax at about the same time as you were at the height of your mathematical powers.
That's true, too. However, it isn't the war that made the physics or the physics that made the war. The wars would have been as bloody without the physics, in my opinion. You will recall that there are 3 branches of physics that I've been stressing. Relativity, that is, the relations of space, time, gravitation, of roughly speaking, the overall structure of the world in the large. Secondly, quantum physics and the principle of uncertainty, that is, the recognition of the fact that in the actions of the universe, the structure of energy is as important as the structure of matter. But we must settle to talk about the structure of matter, because that's a way in which our picture has changed so greatly since the last century. So greatly that it seems fantastic. I would think that in the year, 1930, when I was just graduated, and you were still at school. At that time, in 1930, if you had gone out into the street and said to the first 10 people, "What is an atom?" you would have had 10 stares and no words at all. Today, if you go out and say to the first 10 people, "What is an atom?" you will get 10 answers, all of them wrong, but all of them with some sense that this is a word that they understand, that it says something about the structure of the world. They don't know very well yet, but they're like the contemporaries of Newton who knew about gravitation but didn't know quite what it was. How is that change taking place? Well, it began, of course, in the 1890s, when strange phenomena appeared in thin gases through which electric currents were passed, which in 1897 turned out to herald the existence of particles smaller than individual atoms. Particles that were later called electrons. The fact that they were in electric currents is important because they strongly predisposed every scientist to believe that all matter is really condensed electricity. That's not true, I hasten to say, but that's what we all thought when I was an undergraduate. We all thought that somehow electricity made those smoke rings you're fond of talking about, and they became so tight in the atom that they took on material qualities. And we were so dominated by the idea of electricity that we couldn't make sense of the way the electrons lay inside the atom and went round the nucleus. We couldn't make sense of the nucleus. The nucleus, we said, was positive electricity. The electrons are negative electricity, circling around like a planetary system. Well, the great balloon went up in 1932, when a contemporary of mine, only a few years older, James Chadwick, discovered that that picture was wrong, that there is a fundamental unit of matter inside the atom which has no electrical properties, which is neutral, and which is therefore called the neutron.
But yet behaves like a lump of matter in certain circumstances.
Yes, but it has the great advantage that it is not involved in electrical exchanges. When it is approached by electrons, it doesn't repel or attract the electrons. It remains neutral to them. And when it is linked, as it is in the nucleus, to positive charges, again, it doesn't repel or attract them. It links and forms units with them, out of which matter is made. I remember a broadcast in 1932 or 3, Christmas Day broadcast by Lord Rutherford, who was then the great, grand old man of atomic physics, in which he said, "It may be that we have witnessed the most important discovery in physics with practical consequences in my lifetime." Well, that was a very generous thing to say, because the most important discoveries had certainly been made by Rutherford himself. But Rutherford confessed that this discovery, that matter has a structure which is not wholly electrical, was important. And from 1932 onwards, the neutron suddenly became the darling knife of the scientist. I use the word knife, and I'll pause for a moment in order to explain what I mean. The human intellect, combined with its most powerful weapon, the human hand, has wonderful tricks. And one of them is older than even prehistory. That's the trick of discovering that if you take a piece of wood and you chop it with a stone, then if you go with the grain, it splits open. And if you go against the grain, all you're going to split open is your hand. This idea that matter can be taken apart like a piece of wood along the grain and then put together in new combinations is a very fundamental idea. We no longer think of it as a scientific idea, but it's one of the things which no animals ever thought of. And we wouldn't have houses and metals and television sets and communication, language, if we hadn't made that discovery. So the first cutting instrument which the human mind and the hand has is the stone. The next cutting instrument is fire, chemical analysis. The next cutting instrument is something like X-rays, discovered by Röntgen about the same time. But the cutting instrument of our generation has been the neutron, because with it you can go right into the atom of matter, and you can actually get there because it doesn't bounce back like the stone if you hit the grain the wrong way.
I remember the splitting of the atom when I was a boy at school and you were at Cambridge. And, of course, the neutron really was a cutting tool. I mean, the X-ray was a probe compared to it.
That's absolutely right. That's absolutely right. And not only do you remember that occasion, but I remember it very vividly because that week I went to a Saturday afternoon mathematics class, a sort of tea party that elevated academics have. And a young man came to the class and said, "Have you seen Cockcroft recently?" Cockcroft being a young Cambridge physicist who was busy with that. No, what's special about Cockcroft? He split the atom. Oh, good, we said. Oh, more than that. Cockcroft is terribly pleased. Why is he so pleased? Well, he's going down King's Parade, slapping everybody on the shoulder and saying, "We've split the atom, and all we had was an old tobacco tin and some neutrons, and the Americans have been spending millions." I suppose everybody's spending millions now. The only difference is the Americans are spending billions. Back to the neutron. There had now been discovered within the atom this structure. I referred in an earlier talk to the importance which quantum physics had, which showed that electrons could only occupy certain paths. We now knew that within that, the neutron itself was made up of parts. And I don't think we're at the end of that. I think we now realize that the atom is still a bottomless pit. New forms of structure have to be discovered. But what was the practical outcome of this? Well, there were two very remarkable outcomes. I'll take them separately. One we all understand. We were able to make atomic bombs.
That was totally unexpected until that particular observation about a particular isotope of uranium.
That observation about the isotope of uranium was made in 1938.
Yeah.
But the first patent on the atomic bomb was taken out in 1933 by Leo Szilard, who guessed, as soon as the neutron was discovered, that it would make possible a chain reaction, who wrote a patent specification for chain reaction and presented it to the British Admiralty so that it would remain secret. That was in 1933. One of the least known facts of scientific history. If you split the atom with a neutron, then if it's a heavy atom, some energy will come out as well. The atom will be broken into parts. Now, what Szilard recognized was that those parts may include several separate neutrons. And each of those separate neutrons is capable of going into fresh atoms, breaking them open, releasing some energy, and releasing several neutrons at once, so that the reaction spreads like a chain letter. More and more neutrons go through the thing, and the whole thing blows up. To the end of his life, Szilard struggled against the actual use of the bomb, even though he understood how it worked 5 years before anybody else even thought of it. But I don't want to stop there, because I don't want my non-scientific listeners to lose sight of the fact that with the discovery of the neutron, another great secret was revealed. It's exactly the opposite to the secret of the bomb. The secret of the bomb was that with neutrons you could split the atom open. But the secret that goes hand in hand with that is that once you know that there are neutral particles in the universe, and positive and negative particles, it's only a matter of time before it occurs to you, well, really that means that atoms themselves evolve from very simple ones into very complex ones. Now, you know, that was thought of for the first time somewhere around 1935, 6, I don't remember the exact date. But that was an absolute revelation. I think that in a way we can date all the present interest in biology to that transference from Darwin and evolution as a 19th century idea to the evolution of matter as a great idea in physics in the 20th century.
And the evolution also of what you could eventually call life in terms of physical events.
Absolutely. You see, we start with the idea that out in the universe are floating very simple structures, neutrons, protons, and so on. They come together in very simple atoms, hydrogen to start with. And the universe is full of these floating atoms of hydrogen, terribly thinly spread. I mean, what picture can I give you? If you took a space the size of the whole of Great Britain, let's say 50,000 square miles, that in all that, there wouldn't be as many as 1 million atoms of hydrogen floating about outside in the space. They're as thin as that. But they meet one another, they come together, they collide. What in one of our earlier conversations I called, they marry. And they marry on purely statistical grounds. They build up more complex atoms. First of all, they build up helium. That's going on in the sun at this moment. Where does the sun get its energy? Hydrogen building to helium. Then they build up carbon atoms. And so slowly, the whole richness of the material universe is built up. And with a carbon atom, you also start that chain to life to which you've pointed.
That was the late Dr. Jacob Bronowski in the 5th of 10 conversations with George Steedman. Next week, Dr. Bronowski considers nuclear explosion and describes how the Allies succeeded in making an atomic bomb because they allowed and respected freedom.